Hello everyone, welcome to another problem session. So this is less of a problem than what you might find in textbook. This is a very standard formula. So I just want to talk about some nuances that go with that formula, right? So this is one of the applications of Ampere's law. This is structure that we are describing here. It's called solenoid. So this is called infinite solenoid. So infinite solenoid. There are other solenoids which you can curl them around and then it's not going forever that way. You could have a solenoid that you wind these things like that and go in here in a torus. We'll do this problem later, but this one is an infinite solenoid. It's easier to do. It still has a lot of learning value in there. Okay. So first thing to note is that we are using all this infinite, this infinite, that. There's a reason for using that because of the we're going to use Ampere's law. And you know, the integration in Ampere's law needs to be simple, and the symmetry and the arguments that go with it will make it simple. Okay, so if you know the answer will be the following, right? I'm going to write the answer is this is the way the current is given here like this. So let's see if I had a z axis going that way, and x-axis was going that way, and the y-axis was going that way, and this was a distance s, something within the coils, okay, and maybe s in, and this one was s out. So the answer will be like this. So the answer you already know. Answer will be B will depend on an arbitrary distance. Let's call it S. Some arbitrary point will be a distance S from the cylinder. And this is a vector. So in here, you use a right-hand rule. So each one of the coils, so if the current is going this way, so I go this way, and so it's it's coiling around. So using Biot-Savart law, now on one of the coils, so this is one of the coils. So this is the current going this way. So the magnetic field will be going like that and like coming out like that. So it's going to be rounding around that. Imagine this wire was like that. If that was like that, you can use a right-hand rule, and so this wire will go, if this is the current, then magnetic field would go this way. In the back it will be coming out, and in the front it will be going down like that, right? So using this over here, you can see that magnetic field over, if it's inside, then it's along the k hat. On the outside, we expect to be down, right? So we expect this kind of behavior. But what we get is actually, of course, in the k hat, if it's going this way direction, and mu naught n is the number of turns per unit length times I is the current in each one of the wires. I is the current in each one of the wires. Each one is carrying current I, because it's kind of like a circuit, and I just want it like that. If this point I'm looking at is S is less than or equal to this radius up to which the wire goes, where the current is flowing, and it's a 0 otherwise. And this zero is basically because we have infinite cylinder, okay, infinite system. So if this were finite, then this is saying that you got all this magnetic field. This magnetic field is going. Well, you got a return path. There has to be a return path. So it's saying the return path is the density of these lines over the return path is 0. So all the magnetic field lines has to go through this, but then they return, some will return, so the volume over which they return, or the area of per unit area. So if I were to look at over here, number of lines, there's a kind of vague concept here. The number of lines per unit area of this would be much less compared to number of lines per unit area that's inside the cylinder, and that's why it's representing 0 here. Okay, so that's the answer, and I want you to derive this answer. That's the problem. And the many books have this derivation. It's always good to see how other people derive it. So if you drive yourself and then come back and kind of check how I do it, how I would do it, that can be instructive to you. So this is not so much as a problem as actually reading textbook, help with reading textbook. Okay, maybe at this point I want to remind you to subscribe to this channel. Kind of helps it promote. If you like my explanations, which I'm going to give you now, you can hit the like button. You can also check out my website. Okay, with that done, I'm going to pause it and clean up this place and derive this formula step by step. Okay. Okay, so I wrote up some things. First thing I want to point out is that this is had to do with a tightly wound. The wires are tightly wound, meaning there's no gaps between the wires. That's just a very strange thing to do, and that's for kind of mathematical reasons we want. So if these wires are tightly wound, as if you had a metal sheet and the currents were kind of running on the surface of it. So it will be like currents are running on the surface of it. So it's continuously. And you can say if I take a little band of it, so I put X, Y, Z axis, little band of it, of thick, the height dz, then on the surface there will be some current. I can assign current to this band running left to right in the front like that. That band of the current is like a ring of current, and there's a corresponding ring down here and a symmetric place, and that's why we need the infinitely long. If say infinitely long cylinder, then there will always be a pair of these two, right? If it was finite and it ended up somewhere here, there will still be pair like this. We can always do the pair, but here we will just the pair is coming because it is symmetric, not because infinite. That's what I mean. Symmetric about this O. So I can go a distance z below the origin, and then I'll find another band, and I'll look at them together, creating magnetic field over here. Okay, and that because if I look at the symmetry of the situation along the z-axis, then some simplification will take place. All right. So whenever you apply Ampere's law, there is a Biot-Savart law argument that precedes it. Okay, you have to find the direction of the magnetic field using Biot-Savart law, and you have to find the Amperian loop that you're going to integrate over, right? So you need to find the Amperian loop and shape of the loop and things like that. So pay attention to why I'm going to use the Biot-Savart law. A lot of people just don't really realize that you really need this before you get to Ampere's law application. Okay, so you've seen like people jump right into the loop and then say, how did they get that loop? You may wonder. Well, that Amperian loop they got is based on expectations from applying Biot-Savart law, and that's what I'm going through right now. So if I were to apply Biot-Savart law to find magnetic field there, I'm not going to do it because that integral that I'm going to get is going to be horrendous, but I can get some intuition about what the integral might end up doing. Okay, so over from here to here, I'm going to call it R1 vector. From here to here, I'm going to call R2 vector, but they're at the same distance. These distances will be same. R1 will be equal to R2. Okay, and then the magnetic field at this point will be the summation, which will look like this. Sum of these two from this band and this band will be there. So I'm going to write that magnetic field element. Of course, this is just a Biot-Savart element. Biot-Savart is only true in the integral. Okay, so let's look at how much current that will be. So I have this many loops, each carrying current I, and this many loops per unit length, and the length is dz along this. So that's the current that's going in this band. So I take an element of this band. That element is dl. From here, what's the magnetic field? That's the dB I'm talking about. So for that, I need a dl. dl is, you can see this is d phi, and the radius is r. So it's arc length, but it's in the phi direction, right? So this is kind of cylindrical u hat phi unit vector in the phi direction, which is kind of, if you go in a circle, this xy, and then the phi is that way, and the r hat u hat r is that way, u hat phi is that way. Okay, so like u hat phi is that way, and the x-axis over here, u hat phi is this way, u hat phi is that way. So we had a phi, we have encountered this unit vector before. So it's you can write that in terms of I hat and j hat. The r from here to here will be r of that minus r of that. So this minus that. Actually, this should be exactly opposite. So I have this. Yeah, no, not this. I'm correct. Yeah, this minus that. So this one is sj hat and minus that one. Okay, so this is equal to 1 minus 2. So 2 will be just I got z hat and then that. So I got so this is just a coming from center of this to that point, and then I'm going to the center. So this gives 2 is obtained from some of these two guys, and so that's from this. I'm going to call this R1. The magnitude of this, you can just square magnitude square. You can see what's going to be along along I hat is going to be that. Along j hat is going to be this difference of these two squared, and then we'll get this. And when you expand this, you should get between here and r square sine square phi, you're going to get r square, and s square, you're going to get s square, and then there will be cross product between these two, cross multiplication between these two, sr sine phi. So you're going to get r square will be that, and so this will be same as r1 square, r2 square. Okay. So you also know we need to know dl cross r1 and dl cross r2. This will be inside the your Biot-Savart law. I'm sorry, just I got blanked out a little bit. So if you just do this, then you're gonna have the z's around here. But when you add these two guys, because they're gonna end up adding like that, so we need r1 plus r2. When you do r1 plus r2, you can see z is positive in the r1, but z is negative in the r1. So when I add them up, this z is gonna go away. Other things will all remain the same. So this would just be sj hat, 2 times sj hat, and then 2 times these guys minus 2 times r cosine phi I hat plus r sine phi j hat. And if you want 2r cosine phi sine phi. Okay. And if I do dl, dl cross to get the net magnetic field from these two bands, I'm going to get direction will be in r1 and r2 direction. So we are going to get a really strange looking expression, but all will be in k hat direction. So it's because this is I hat and j hat only, and this is I hat and j hat only. So we are going to get I hat go with the j hats. So I'm going to add a k hat direction, and you can see there's r factor, and then there is a 2 times r, 2 times r factor. So I hat with a j hat is going to be minus k hat, so it's going to be minus, and that's going to be s and sine phi. So with this and with this is going to be there's a minus here, and this is going to be plus r sine square phi. So that's coming from this guy cross producting that guy. Now this one cross producting into this will be this j hat, so it's only going to be with this. J hat cross I hat is minus k hat, and with this minus becomes a plus k hat, so this is going to be plus, and then I have a r and cosine square phi. So this just turns out to be k hat two times r minus s sine phi plus r. So this is in the direction of k hat, and so if I put all of this in here, I get mu naught n I over 4 pi, and I have a 2 times r, I have a k hat, and then integrate over dz, integrate over d, there's a d phi missing, there's a d phi here missing, integrate over d phi, and I've got really this guy r minus s sine phi divided by r cube, and that's r square plus s square plus z square minus 2sr sine phi 3/2. Okay, so we have this. We can definitely know it's along the plus or minus k hat direction. So magnetic field over here, let's pick another ink to indicate that. So magnetic field over here is either that way or that way, depending on what the answer for this is. Now the answer of this, say this is positive or negative. It's going to be answer will be positive or negative. So one way to kind of see which way that will be is to just use right hand rule from here. So from there, use the right hand rule, you would get that this direction is this way over here. If it's at all, it's going to be down in along the z hat direction. So that's a direction. Another thing you can see here is although dz is going to from minus infinity to infinity and dphi is 0 to 2 pi, this integral is really hard to do in general. You might be able to do this integral and get some answer, but in general it's very hard to do. You might try doing it, I don't know, but I would not recommend that. It's because of sine phi down here. Okay, what else can we do? Now this is sufficiently regular that if I wanted to see what will happen way out there, if this point was very far on the y-axis at infinity, then I could actually simplify this thing. Okay, let me, assuming I've done this correctly, so this is not equal to that. This is actually b, this thing, when I integrate it, this is b at some point s, and there's, you know, y-axis is nothing very special here. It can be any point on a distance s away in any direction, right? So what if happens is b s is greater than r we're looking at, and if I say limit s go to infinity, well, you know, sometimes you can't switch the integrals with limit, but suppose we could, there is a possible, suppose we could, then this will go to mu naught ni 2r over 4 pi k hat, and I got to do dz integral, I got to do dphi integral. You can see the as z goes to plus minus infinity, this integrand is pretty going to 0 actually. That's one of the reason I can switch the integrand and limit. Okay, and then say if I can do limit first of this, say number 3, that expression 3, well, you can see what this will be. Limit of 3 as s go to infinity, that's going to be, this will dominate, and then this will dominate. So this will be minus s sine phi, and down below is s cube. So this goes to 1 over s square sine phi, which goes to 0. So this will go to 0. So we can claim that b s go to infinity. So if I go any direction outside, I go to all the way to infinity, then it's 0. Now we claim that, okay? But we still don't know what B of S is. I'm for S finite. What about S finite? And then I'm gonna play a trick and find S finite, okay? So this is a point outside. So let's call it this y-axis point. This is the this is a point here. So I want to know what the B in this situation is. Well, from the symmetry and argument, so if I stay on this, so all of this, if I same distance away from this, now I'm going to say, because the cylinder is infinite, all of these points are equivalent. So B here, so this, say this is the S, this B here at point P is the same at point A, at point B, and so we also know that over here this is S equal to infinite, okay? Over here B is Bs equal to infinite is 0. So now I can apply Ampere's law in a loop. The B is going this way, so I just go along the B and I go this way, and then I go this way. So this is a mathematical loop in space, and let's see this B distance L, okay? So I don't know what B is at point P, so B dot dl in this loop, and inside here there's no current going through here, so this will be equal to, on this loop, A B C D A is equal to 0, since no current enclosed. So now go through this. A to B is B in, I'm going the same direction as the K, so the perceived B is supposed to be in this direction. So B supposed to be in that direction, and DL is in that direction. So B at P times is going to just give me L plus 0 plus 0 on B to C. This is on A, B, and this is on B to C. Now here the DL is this way, while assumed B is that way from this formula. And this because B is perpendicular to DL. So the dot product is 0 at all points of B to C path. A to B is 0 because B is 0 there. B at infinity is 0. And if I go B, we're calling C, this is calling D, and then D to back to A. Now this is B is supposed to be that way, the DL is supposed to be that way if I look at a small element, and so this is going to be 0 again, plus 0 because B is perpendicular to DL, and so that's equal to 0. Right, this is right side 0 and this is left side. So there's only one term. The L is a completely arbitrary length loop I'm looking at, right? So this just simply just say B for any S, that's B for any S between R, S, infinity is equal to 0. And 0 vector does not require direction, so no direction information needed. So B out equal to 0. So outside an infinitely long cylinder in which everything is wound very tightly, okay, this is tightly wound, went into our converting this to a continuous current on a surface. So for tightly wound, for this assumption, B out is 0. Okay. Let me erase this and let's look at what will happen inside. Okay, so to look at the point inside, so we want B at S less than R. So this is inside. We're not looking at B at S equal to R yet, okay? So, so this is some point here. So how do we get? Well, from outside is 0, so over here is B is 0. So if I look at it, magnetic field is, using a right hand rule, so it's going up, magnetic field is going up, magnetic field is going up in that way. From this also, from Biot-Savart law, so magnetic field is going up. So I need to think of a loop in which I can find the magnetic field at that point, the magnitude, we know the direction. So the loop will be, but again using the symmetry, so using symmetry, so this is at some point S symmetry, all of these points which are all distance S away should have the same magnetic field. Using symmetry, claim, now I'm going to call it, this guy call it A and this call it B, all points at a distance S from Z axis have same B. So this will be on this B dot dl, on the AB part will be B is the same, dl is in the same direction, so this is going to be B times, let's call this L also, so this will be BL. But this is not a closed loop yet, so I need to think of a closed loop, and it suggests that I go through here and so that I can enclose a current. Now I want to enclose a current. I want to take a loop that encloses current. So if I do it out, if I go this way and I go this way and this way, so now if I go this way, then if you look at the orientation, so the loop orientation, if you remember, has to be such that if I go in the loop this way, then that direction is positive current or area direction, okay? So like coming out. So for instance, if I show you an oriented loop like this in a space, then you may be able to see it better. So if I go this way in the loop, in a loop, this Amperian loop, then the inside area is positive that way. So this is using right hand rule. So I go around, and wherever the thumb points is the direction in which I would have a positive area or positive current. So if the current flowing in that direction, I'm going to add. If the current is going in that direction, I'm going to subtract. Okay, so in this one, let's go through A, B, and then I'm going to call it this C and D. So the loop is A, B, C, D. So this loop A, B, C, D back to A is equal to A, B plus BC plus CD plus DA, back to DA. So this part we just talked about is going to be B at that S times the length of this loop. Over here is going to be 0 because D, just like the last time, DL is this way, but the B maybe over here. Over here is B is 0 from outside, B is 0. So this part is going to give me 0. How about this part inside? The inside is DL is perpendicular to B. So DL is this way, DL is this way, and the B is that way. So this is going to give me 0. So that can give me 0. And then C to D, B is 0. So that's going to give me 0. D to A is the same situation as that. This will be 0 because B is 0. And this will be 0 because B is perpendicular to DL. This is 0. So that's we got B times L on the left side of Ampere's law. And then that should equal, so this should equal mu naught times I enclosed. So we need to figure out how much I is enclosed. So we need to count how many loops that went through this area, across that area. And now the length is L, and we have n turns per unit length. So that would mean that I've got n turns times the length, and for each turn I got current I. Okay, so I have a mu naught B times L is mu naught n, and so L can cancel out. So B of S less than R, that's when current is enclosed, and that's equal to mu naught Ni. Okay, now you say we did S greater than R, and that was 0, B was 0, S less than R, and that's the B is mu naught Ni. How about S equals to R? That's the only point. So if I'm right on the wire, what happens? And let's address that question, because that's often kind of not addressed, right? So we're going to look at that, S equal to R. What is the magnetic field right at the wire? Okay. Yeah. So so S equal to R. So for that we need to know that if you look at B dot dl equals to mu naught I enclosed. So this is on the loop, right? This is going to go on oriented loop, and this is actually inside the area, not counting the loop. So this is actually refers to passing through area not including the boundary. So, and that comes from Stokes' theorem. I haven't related this to the Stokes' theorem, but the Stokes' theorem kind of has this thing just inside. So if I have this my C, then this is area is the open set here, not including C. You can get as close to C as you want, but not the C. Okay, so how do we address that? So here is let's look at this cylinder again, and I'm at that C. So if I'm at the C, and let's look at this loop. So I'm at the C. So over here, let's call it A, B, C, D. So, and this is the L. So this is B in times L this side. That's this formula. And plus 0 plus, we don't know what that is, plus B at, exactly at, times L, and then D to A plus 0. But now, because I'm at that, you look at this, no, I enclosed is 0 because this boundary, the current is right at the boundary. This is all mathematical things. So this at the boundary, so that's equal to 0. So this added up should equal to 0. So L is this way, DL is that way. Oh, so this is going to be so I made a little bit of mistake here. We should do it. This is k hat direction. So this is k hat dot B, and so this will be DL, this will be minus here, and we're looking at Z component. We're looking at Z component like that. So because DL is opposite to the K, so the way I'm going is just exactly opposite. That I should have drawn something more like this. So we just look at the Z component, right? Because you're doing DL dot B, and DLs are either negative Z or positive Z, and so that's why you have a negative positive here. And we're just looking at the Z component we're getting. There's no X and Y component here. So when look at B at, its Z component is equal to B in its Z component. So it seems like this is actually same thing as mu naught and I. So let's complete this by recapping it. So we have B is equal to 0 if S is greater than R, is mu naught K hat mu naught Ni, K hat if the currents are going this way, minus K hat if the currents going the other way. Okay, so this is check right hand rule. Otherwise, it's going to be plus or minus K hat. S is less than equal to R. And so we got all the answer. Now you can get that answer if you were to somehow integrate this thing. You will get some simple answer like that. It's possible to recover from it, but it's normally I know this integral is it's extremely hard to do. Okay. I just want to stop here now, and I'll talk to you in another video. It is a very long video, and it's an important case to understand various aspects. Okay, bye.